In this video, we're going to apply Coulombs law, but collinear forces. In the next video, we'll talk about when we have to use vectors. We'll actually be using vectors in this situation, but we won't have to find components. We're just going to think about direction. So let's start off where we have two forces or two charges that are going to attract each other. So I'll put the red ones, we'll make these negative. So let's say -2 microcoulombs, and then green will be positive charges. So center that one. And let's say +3 microcoulombs. And we want to find the force of attraction between the two. We'll need to establish a distance, of course, so a distance between their centers, and let's say 10 centimeters. Okay, Coulomb's law looks like this. K Q1 Q2 over R squared. A really interesting property of inverse square laws, just to do a little calculus connection, is that why inverse square law? Well, if we look at the limit as R goes to infinity of 1 over R, it turns out that that is undefined. But in the limit as R goes to infinity 1 over R squared, that's 0. So from a calculus point of view, the reason this is the first order of magnitude in which we see that the force actually has a place where its influence is 0. And that's a really important point from a cosmological point of view. At any rate, in this case, we can go ahead and start putting in numbers. So this first time I do it, I'm going to include units. So this is 9. It's 9.0, but 9 times 10 to the 9th. And then having units, so that the final outcome is going to be left with just newtons. So that's our value for K. And then we have these two charges up here. So microcoulombs is 10 to the minus 6. So 2 times 10 to the minus 6 coulombs, and then 3 times 10 to the minus 6 coulombs, and then divided by the distance. And SI units, so this is going to be 0.1 meters, so 0.10 squared. So we'll assume 2 significant digits for everything. Okay, great. So how do we evaluate that on the calculator? Okay, let's bring the calculator in. So I'm going to use 9 times 10 to the 9th a lot in this video. So what I can do, I can actually store that as a variable. So this is on a Texas Instrument calculator. This is how we do scientific notation. We use the double E button. It's problematic to use this key over here. It's problematic to say 9 times 10 raised to the 9th. And the reason why that, I mean, it's still correct. It's still going to give me the same number. But the reason why this is better is because it's going to cut down on the need for parentheses when we get into more algebraically complicated situations. But like I said, I'm going to use this a lot. So I'm going to store it as the letter K. Then in the future, all I have to do is call up the letter K. And there it is. So that's handy. All right, so let's proceed then. So this is K times 2e minus 6 times 3e minus 6 divided by 0.1 squared. Okay, and we get 5.4 newtons. So a couple of things to point out here. And let's check that the units cancel out the way they're supposed to. So Coulomb squared. I forgot to write meters down here, but meter squared. So we're just left with newtons. So that checks out. And then the other thing too is why didn't I put in a minus sign for the 2? And there's a really important reason for that. And it goes back to Newton's third law. So this, since they're opposite, we know they're going to attract. Frequently, we just apply the logic in our head that this is going to feel an attractive force of 5.4 newtons. And then this will feel an attractive force of 5.4 newtons in magnitude. But if we were going to write this as a vector, we would say that it's a vector that points to the right, and this one is a vector that points to the left. And putting a minus sign here is just going to give us a minus sign in the answer, but it's not really going to give us information about these. So when we're doing these collinear forces, let's just use logic to figure out which direction the forces are going to be instead of relying on the algebra. So that's the big takeaway. Okay, in this next example, let's put 3 of them there and see what that looks like. So we're going to need some space for this example. So let's go back. Let's do our -2 microcoulombs. And then our +3 microcoulombs. And then let's put in a third charge, and we'll make that negative. And we'll make this -4 microcoulombs. So these 2 negative charges are going to be playing a tug of war on the middle charge. And again, we'll assume the distance between each is 10 centimeters. So in general, in these videos, the reason why I'm taking the time to draw everything out is also to give you the time to draw things out. And I would really encourage you to do that, because taking the time to let the physics come through your fingertips is really important. And in education terms, we call that internalization. Or some people just call it muscle memory, right? So sometimes if it's hard to know where to start, maybe your hand will know where to start. Okay. So in this situation, we're going to find the force that's acting on all 3. And we assume that there's some kind of magic glue that's holding them all and keeping them from moving, but let's find the forces. So forces on the -2 microcoulomb. All right. So by +3 microcoulomb, we already did that. And so we know the force that's caused by the 3 microcoulomb charge is going to be plus 5.4. And just to be double safe, it's to the right because it's an attractive force. Now the force by the -4 microcoulomb charge is going to look like this. So we're going to have K times 2 microcoulombs times 4 microcoulombs. So that's bigger than the 3. So maybe it wins. Microcoulombs. And now the distance is double though. So this is going to be 0.2 squared. Okay, now a nice thing about our calculators is that they can remember what we just did. Whoops, not that way. Right, so now I can just go in and change the numbers. So that's now going to be a 2, and this is now going to be a 4. Okay, so 1.8, and it's much less, even though the charge is bigger, it's because the distance is double and the denominator is squared, so it makes it much less. 1.8. Now this is a repulsive force, so the force on this charge due to this charge is going to be that way because they're repelling each other. So I'm going to write minus because it's to the left. And then our total is now 5.4 minus 1.8. So the force by the middle charge wins And so 3.6 to the right. And I'm positive about that. Ha ha ha. Okay, so now let's try forces on the positive 3 microcoulomb. So the force by the negative 2 microcoulombs is, well, we've already done the math on that. And it's pulling it to the left. So we're going to write minus 5.4 left. And then by the negative 4 microcoulombs, so we're going to have K times 3 microcoulombs, and then times 4 microcoulombs divided by, and this is only 0.1 squared. Okay, so we'll ask our calculator to repeat that calculation that we just did a little bit ago. We'll go in here and change our numbers up. So now this is 0.1, and I'll keep the 4, but I'll change the 2 to a 3 and hit enter. Oh, it's big. Okay, now what direction is it? Well, it's an attractive force. So that's going to be a force to the right. So that's going to be plus 10.8 to the right. So again, I'm going to subtract. Yeah, not a big surprise there. So plus 5.4, and that's to the right. Okay, good. Now again, just hammering the point, that's why we don't put in pluses and minuses when we're applying Coulomb's law. We just apply logic to see which ones are working together and which ones are in opposition. And so finally, to finish off, let's do forces on the negative 4 microcoulomb charge. All right, so we'll do the force by the negative 2 microcoulomb charge, but I think we already did that, right? It's not going to be the same number as this over here, the 1.8. By which direction? Well, they're repelling each other. So that's going to be positive 1.8 because it's to the right. Again, Newton's third law, equal but opposite directions. And then by the positive 3 microcoulomb charge, well, we already did that too. That's this one. And so that came out as 10.8. But what direction? Well, it's an attractive charge, so it's actually to the left. And so we'll make this negative. Right, once again, Newton's third law, equal and opposite forces. Okay, great. So what's up? Well, 1.8 minus 10.8. Yeah, minus 9. And that's a force to the left. Okay, so that's how we deal with collinear forces.